All right, so good day everyone. I'm Norman Wildberger. Today we're going to start this very short little course on probability and statistics. Okay, and we're going to be covering roughly topics in this direction. Some set review, basic counting, talk about probability and odds, random variables, probability distributions. We'll look at the very fundamental notions of mean and variance of a distribution. Then we'll talk about some special distributions, the binomial, Poisson, and normal. And talk a little bit about the central limit theorem, which is sort of the main theoretical result which sort of looms ahead. So it's a rather theoretical course. We're not going to be doing too much practical stuff. It's a rather short course. And I'll be moving along at a fair clip, but hopefully not too much. And students in the class, don't be reluctant to ask questions and such. Interrupt me, that's no problem. All right, so today we're going to start with a basic review of sets to start with. So let's just remind you of a few things about sets. So first of all, what is a set? So a set, say A, is a collection of some kind of usually mathematical or maybe everyday elements. So for example, we might have A is the set 1, 2, 5, a triangle. Okay. That's our usual notation. We have these brackets, braces to denote the extent of the set. The objects in the set are called elements. The total number of elements is called the size of the set. So the size of A, we usually denote that just by A with absolute values. That's the number of elements in the set A. So in this case, the number of elements is 5. And then there are operations on sets. So maybe we'll go over here. There's a kind of algebra of sets. Operations. Well, the main operations are union and intersection. So the definitions of those, if A and B are sets, then A union B is the set of all X such that X is an element of A or X is an element of B. All right, so here's our standard formulation for sets. So this is describing the objects that are in or comprising the set, and this is the condition that those objects have to satisfy to belong to the set. So this line here, or often two dots, means such that. And the epsilon is the containment relation, means that X belongs to A. So for example, or maybe I'll do the intersection as well. So A intersect B is the set of X such that X is in A and X is in B. So for example, if A is our set, same one as there, 1, 2, 5, A and triangle, and B is the set 3, A, triangle, 7, well then the union is everything that we get by choosing something in the first set or in the second set. Notice that we don't repeat things. A set can only have one of each element in it. Okay, so we're not repeating any elements. So this thing consists of all those elements which are either in here, and that or includes possibly being in both. So A, for example, is in both sets. That's all right. It's still an element of the union. And the intersection, well, the set of things that belong to both A and B, that's the common elements, which there's A and triangle, I suppose. Sometimes we have what's called a Venn diagram to illustrate sets, give us a picture, what's going on. So Venn diagram, maybe this is the set A, and this is the set B. It's just a diagram to illustrate things. Well, then the intersection is this part here. So that's A intersect B, while the union is just things which are in the whole thing like this. So that's A union B. And now sometimes our sets all belong to a universal set. Maybe all the sets we consider belong to a fixed universal set, usually denoted U. All right? So in that case, we think of U as being the box. And if we have a set A inside it, then we can also define the complement of A. So in this case, A complement, with a little c there, means the set of all x that belong in A such that x, no, the set of x that belongs to U in our big space such that x does not belong to A. All right? That's called the complement of A. And that, of course, is the outside in this picture. So there's A complement. Combining these things, sometimes we can talk about the difference. So A minus B. By this we mean this is a set of things that x such that x belongs to A and x is not an element of B. And we would picture that with a Venn diagram. Perhaps there's A and there's B. So then A minus B will be everything that's in A which is not also in B. A minus B. All right, so that's good. Those are some basic definitions, really. Now let's have a look at some basic laws. All right, there are various laws of set operations. We're not going to worry about all of them, just point out sort of mainly the sort of non-trivial ones are sort of distributive laws, which say that A union B intersect C equals A union B intersect A union C. And there's another one, opposite law, where the unions and the intersections are interchanged. So A intersect B union C equals A intersect B union A intersect C. And these are called distributive laws. Because they're supposed to remind you of the law that for arithmetic, that A times B plus C equals A times B plus A times C. So have the same form as this one does. And how do we prove one? Well, we could make a diagram and have a look diagrammatically. So here we have three sets, A, B, and C. And let's calculate the left-hand side, say of the first one, and then the right-hand side, and see if they're the same. All right, so what would that look like? The left-hand side would be A union B intersect C. So we're taking everything that's in A or in B intersect C. So B intersect C is in here, and A is right here. So everything that's in A or that's in B intersect C. That's the left-hand side of 1. All right, and now in blue, I'm going to compute the right-hand side of 1, which is the intersection of A union B with A union C. All right, so where's A union B? Well, it's everything that's in A and in B. So everything in there. Okay, and then we have to take the intersection of the union of A and C. Where's A and C? Well, it's this thing here. So maybe I'll okay, so we have to take the intersection of those things, the things which are common to the dots and the crosses. And if you look at it for a little while, I think you'll convince yourself that it's this stuff here. Convincing ourselves that, yes, the first law is true because the two sides are equal. And I'll leave it to you as a little exercise to convince yourself of the second one. All right, good. So the next order of business, inclusion, exclusion. Very important law for counting with finite sets. All right, so there's a baby version and a more adult version. So the first version is that if you have two sets, A and B, then the number of elements in the union equals the number of elements in A plus the number of elements in B minus the number of elements in the intersection. And why is that? Well, when we count the number of elements in the union, we could count all the elements in A, count each one of them. And then we could count all the number of elements in B, count each one of them. We've counted everything, but some of the things have been counted twice. The ones in the intersection have been counted twice. First in the first count and in the second count, so we have to subtract them from the grand total to get just everything counted once. Okay, so the more sophisticated version is when we have 3 sets, in which case we have A union B union C. The number of elements in the union of 3 sets is the number of elements in A plus the number of elements in B plus the number of elements in C minus the number of elements in A intersect B minus the number of elements in A intersect C minus the number of elements in B intersect C plus the number of elements in A intersect B intersect C. That's a little bit more sophisticated, so let's see why that's true. So here's A, B, and C. We want to count how many there are in the union. So that means we want to count inside the big collection, but we want to count everything just once. All right, so the first thing we do is we count all the A's. All the things in A. That's the number of elements in A. So we're counting all the things in A. Then we count all the things in B. Some of them have already been counted, but we're counting them a second time. And then we count the things in C. We'll count the ones that have already been counted, as long as they're in C. Okay, obviously we've overcounted. We've overcounted because the ones in these intersections have been counted more than once. So we're going to subtract the number in here, and the number in here, and the number in here, to compensate for that fact that we've been double counting. But now we're subtracting the ones that were here. We've counted them twice. No, the ones that are in here, in the middle, were in all 3 sets. So they got counted 3 times at first. But then we subtracted them each 3 times as well, because we'll subtract them once for each one of these. So we counted them 3 times, and then we subtracted 3. Now we still have to count them because we want them to count. And that's why we add the number in the intersection at the end to make sure that we've counted everything exactly once. Any questions? What do you think the inclusion-exclusion looks like for 4 sets? Is it obvious to you what it looks like? What about if you have 10 sets? All right, so as an exercise, work out inclusion, exclusion for n sets. All right, so let's do an example. Okay, so we have a university swim team. So the uni swim team has 11 students taking chemistry, 12 taking maths, 12 taking physics. If 7 take, let me abbreviate these by C, M, and P. So if 7 take C and M, 4 take M and P, maths and physics, and 5 take chemistry and maths. And if 3 take all 3 subjects, how many are on the team? Yeah.
Should be CMP.
CMP. Oh, okay. So right, 7 taking chemistry and physics. Yes, thank you. 7 taking chemistry and physics. 4 taking maths and physics. 5 taking chemistry and maths. Thanks. And 3 taking. I should. One more fact that I need to tell you. 3 taking all 3 subjects, while 3 are taking none of these. While 3 take no subjects, or take none of these. And this is the question, how many on the team? Okay, here's a universal set. It's the swim team. And on the swim team, we're imagining we have 3 subsets. The ones taking chemistry, maths, and physics. So one way of working this out, if if you didn't know the formula, you could just say, all right, let's see if we can fill in the information on this thing. We know that there are 3 which take all subjects. So I'm going to put 3 dots here representing the 3 individuals which are taking all 3. Okay? So we know there's 3 taking all 3 subjects. We know there's 3 that take none of them. So there's 3 that take none. They're outside the 3 sets. What about this information here? There's 7 taking C and P. That means in the intersection of C and P, which is that one there. So here's the intersection of C and P. We know there's a total of 7. Well, we've already accounted for 3, so we need 4 more. Between P and M, we know there's a total of 4, so there should be 1 more. And between C and M, there's a total of 5, so we need to put 2 more. Okay, what else do we know? We know these 11 students taking chemistry altogether. So in the chemistry set, there's altogether 11. We've already accounted for 4, 7, 9, so I guess there'll be 2 more. Altogether, there's 12 taking maths. We've already got 2, 3, and 1. That's 6 already. There's 6 more that are just taking maths. And of the 12 students taking physics, we've got 8 of them counted for, so altogether we've got 4 more. All right, so we could say, well, without any formulas, we could say, all right, now the total number of students must be, we have to count them. 3, 4, 7, 8, 11, 15, 17, 19, and 6 is 25. All right, let's see if we get the same formula with the inclusion-exclusion rule. What's that tell us? It tells us that the number of elements in C union M union P equals the number in C plus the number in M plus the number in P. Whoop. minus the number in C intersect M, minus the number in C intersect P, minus the number in M intersect P. Plus, not to forget, the number in C intersect M intersect P. Okay, what do we know? Number taking C is 11. Number taking M is 12, and the number taking physics is 12. The number taking C and M is 5. The number taking C and P is 7. And 4 taking M and P. And how many taking all 3? We're told that's 3. So we have to add 3. For a grand total of, this 12 cancels with that 12, so we've got 23 minus 1, that's 22. What's that? So that's the number in the union of C, P, and M. And therefore the total number in S is the number in C union M union P plus the number in the complement. So we've just calculated that there's 23, and we're also told that there's 3 which take none of them. We haven't used that so far, so we have to add that for a total of 25. So looks like everything is all right. Okay, another useful notion for us is the notion of a partition. Partition of a set. Okay, so the idea of a partition is just as the English word suggests. We have a set A, and we're going to subdivide it into pieces. So we're going to, that piece, that piece, that piece, that piece, that piece, that piece, that piece. Right? There's a partition of the set into different pieces. Let's say A1, A2, A3, A4, A5, A6, A7, in this case, 8 subsets. So what is the definition? A partition of a set A is a set of subsets A1, A2, up to, say, AK. Okay, what does a subset mean? I haven't mentioned that before. So we say, C is a subset of B. Say, C is a subset of B. What that means, it means that if X belongs to C, then X belongs to B. So we have 2 sets. One is a subset of the other. If being in the first set, it immediately implies that you are also in the second set. In that case, the first set is a subset of the second set. So to continue with the definition, a partition of a set A is a subset of set of subsets, A1, A2, AK, so such that 2 things. The AIs are all disjoint. What does that mean? It means that AI intersect AJ, the intersection is always empty. Okay? So we write the empty set with braces with nothing inside. Okay, that's the empty set. Another standard name for the empty set is a phi. That's just another common name for the empty set. So it means that, as here, none of these sets overlap. They don't have any common elements. That's the first condition. And the second condition that a partition has to have is that it has to fill up all of A. Everything should be in at least one of the subsets. So we want the union A1, union A2, union up to AK to be equal to the big set that we're starting with. So here's an example. Let's flip a coin. Flip a coin 3 times. Okay? Then the possible outcomes of that experiment are represented by the set. So here's the set of possible outcomes. And I'm only interested in tails or heads. So tail, tail, tail. That means first one was a tail, second one was a tail, third one was a tail. Or we could have tail, tail, head, or tail, head, tail, or tail, head, head, or a head, tail, tail, or head, tail, head, or head, head, tail. How many do we have so far? 1, 2, 3, 4, 5, 6, 7. Any more? All heads. Yes. Any more? Those all the possible outcomes? Yes. We know there's 8 possible outcomes, right? Because every single time there's only 2 possibilities. So altogether there's 2 times 2 times 2 equals 8 possible outcomes. All right, so that set kind of captures the set of all possible outcomes to this experiment of flipping a coin 3 times. Now let's consider a partition. Okay, I'm going to partition this set. Well, maybe I'll just call them yeah, okay. Maybe I'll write the first one A0. So A0 will be the set T, T, T. A1 is the set T, T, H together with T, H, T together with H, T, T. A2 is the set T, H, 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 T, H, and H, H, T. And A3 is the set, there's only one left, H, H, H. All right, so I guess you can see what the pattern is. I've said that the pattern is that AK is the set of outcomes with exactly K heads. Yes? I've grouped all the outcomes with the same number of heads or the same number of tails into one little subset. So here are 4 subsets of the original set, And we claim that the set A0, A1, A2, up to A3, this is a partition of the big set A. Okay, and what does it mean? It means that, first of all, they're all disjoint, right? No, there's no overlap between these sets. And together, the second condition, the second is that altogether we get the whole set A from them. All right, let's talk a little bit about functions. All right, have to review a little bit of notation with functions and the relation with functions and sets. All right, so we'll suppose that A and B are sets. And f from A to B is a function. That just means that it inputs an element of A and outputs an element of B. So associated with this, we can define the image of f. That's a familiar idea from linear algebra. The image of f is the set of B in B such that B equals f of A for some A in capital A. That's one thing that we define. And another thing that we define is for each B in the second set, we define the inverse image, f inverse of B, to be the set of A in A such that f of A equals B. And for a subset, for let's say E a subset of B, so for E a subset of B, I'll remind you that's what it means. E is a subset of B. We define f inverse of E to be the set of A in A such that f of A belongs to E. So let me illustrate it with a toy example right here. So here's a set A, and it's going to have elements A, B, and C. And over here is a set B, whose elements are 1, 2, 3, and 4. And I'm going to define a function, f, from A to B, just with some arrows. So I'm going to declare that A goes to 2, and B goes to 3, and C goes to 2. Here's my function. Okay, so first of all, what is the image on the function's name is f? So what is the image of f? Well, according to the definition, it's a set of B in B such that B equals f of A for some A. So it's a subset of B, It's those things in B for which there's something in A that gets sent to it. So that's just the set 2 and 3. Those are the elements in B that actually get hit by something in A. Let's take an element of B and look at its inverse image. So F inverse of 1 is, what are the things in capital A that get sent to 1? Well, nothing gets sent to 1. That's an empty set. I'll write it like that. How about F inverse of 2? What gets sent to 2? Well, both A and C do. So that's A, C. It's a subset of A. What about F inverse of 3? Well, that's just the set B. And let me do an example of the inverse image of a set, a subset of B. Let me take the subset. Okay, I'll choose this subset. Okay, that's going to be the subset E. So what would then be F inverse of E? So it's all the things in here that get sent to some element of E. That gets sent to an element of E. That does not. That does. So it's AC. Okay, so here's a proposition. If f is a function from A to B, where A and B are sets, and suppose that E1, E2 up to EK is a partition of B, then F inverse of E1, F inverse of E2 up to F inverse of EK is a partition of A. Let's have a look at this result. If F is a function from A to B, A and B are sets, and we have a partition of B, the second set, then if we look at the inverse image of each one of those constituent subsets of B, the inverse images form themselves a partition of the first set A. So the picture is, here's our set A, here's another set B, we have a function F, we have a partition of B into these sets E1, E2, and so on up to E, say K. And then what we're doing is we're looking at the inverse image of each one of these sets. We're claiming that if we look at the inverse image of E1, maybe it's like this. So there's F inverse of E1. And maybe this is F inverse of E2 over here. And carry on. So eventually we get to F inverse of EK. That the inverse images of these sets form over here a partition of A. So let's prove it. Let's write down a proof. Well, first of all, let's note that F inverse of EI is a subset of A for any I. It actually is a subset of A. That's the first ingredient to have a partition. We have to make sure that these are actually all subsets of the set we're talking about. Now, what do we need to know about those subsets? We need to prove that two things about them: that they're disjoint and that their union is the whole space. Well, okay, disjoint. So claim F inverse of EI is intersect, well, I'll say, is disjoint from F inverse of EJ if I does not equal J. Well, if A belongs to F inverse of EI and it belongs to F inverse of EJ, then what does it mean? Well, if it belongs to F inverse of EI, it means that if you apply F to it, you end up in EI. That's what it means to belong to F inverse of EI. So the first condition would be that F of A belongs to EI. And the second condition would imply that F of A belongs to EJ. But that's impossible because we're assuming that E1 up to EK is a partition of B. Right? This is impossible since E1 up to EK is a partition of B. And that means that no two of these subsets overlap. So we can conclude that F inverse of EI intersect F inverse of EJ is the empty set if the I does not equal J. And the second thing that we need to show is that the union is all of A. Okay? So if A belongs to capital A, does it belong to one of these F inverses? Well, yes, it does. Then A belongs to F inverse of EI, where which one is EI? So if I pick an element A in here, I want to know which inverse image does it belong to. I just apply the function to find F of A and see which of these guys this F of A belongs to. So then A is in F of inverse of A, where F of A belongs to EI. So the union, so F inverse of E1 union up to F inverse of EK is all of A. All right, so that's good. Next time we are going to start with some basic counting and probability. So I'll see you then.